books starting to talk. It's some kind of theoretical antenna. It's called Hertzian dipole. So it's very short uh, element of wire uh, infinitesimally thin, and uh, so due to that, it is very short. Um, the distribution of current is the same through all these length of course, very short length of this theoretical antenna. But from this small theoretical antenna, if we know how the electromagnetic field is distributed uh, some uh, in some point in the space, um, we will divide real antennas, divide into very small parts, and in which these parts, all these parts is consisted from the small Hertzian dipoles. And if we sum all these electromagnetic response in some point, we will have electromagnetic response of real antenna. So the Hertzian dipole is an antenna consisting of an extremely short piece of straight conductor that carries an alternating current, which is a consequence of its short length, is uniform over the length. So this alternating current is uniform over that length. So it is very important because it is much easier to calculate the electromagnetic response, and it holds this condition if it's very short length. Okay. So in order to ensure that the current distribution is uniform, just a moment, sorry. Okay, so in order to ensure that current distribution is uniform, the antenna is assumed to be electrically short. So this concept is very useful in the study of many real antennas of finite length. So since these may be regarded as having equivalent properties to a summation of a number of short dipoles connected together with their radiation patterns deduced from knowledge of their geometrical disposition and superposition of the basic Hertzian dipole radiation pattern. So if we assume that Hertzian dipole is excited as a sinusoidal current, which is uniform along its length, delta L, oriented along the axis X. So you can see here, it actually, we use like an alternating current, how we express our alternating current. Here we have amplitude, and here we have the phase of our alternating current. So I should try to write on the desktop. This is not very easy with using just only touchpad in my case, but anyway, we should try to write some expressions, and please write it because was easier to understand uh, from where some expressions comes. Uh, so, okay, now we will go to, okay, here we should a little bit, here we a little bit stop, and I will try to share, okay, the desktop. So, uh, the current flowing in antenna consists of some number of electrons, each of charge um, will will have some kind of velocity, and in time this velocity change and would flow through the length of the antenna. So hence, since current we can define, so the current E we can define as uh, some differential of our charge. Oh, it's not easy actually. Q, yes, and divided by some kind of differential of time. Okay, so you can write on the paper much easier and more nice. Yeah, okay. So this part we can change the number of electrons and velocity, yes, and of course charge. So we have number of electrons and multiplied by our charge Q and multiplied by the velocity V, and it should be divided by the length of our antenna, delta L. Okay, so and all these should be equal to the alternating current, which is actually moving our electrons in the antenna. So it means that we have current with index 0, and we have sinus function, sine omega t multiplied by the time. So then, from this, we can extract velocity. So v will be equal to oh, it's almost nice. Okay, so delta L multiplied by current E sine function, sine, it means that omega t, yeah, that's some kind of touch pad, maybe it's better. Okay, Anyway, and divided by number of electrons divided multiplied by the charge Q. Okay, so now if we will differentiate the velocity, you know from the mechanics that we will have acceleration. So acceleration A is equal, oh, what's that? What's wrong now? Just a moment. Okay. Draw. Okay, now something stupid. So how I can check? Sorry. Draw text. What's mean text? Maybe I can write just only the text. Okay, let's see. So A is equal to divided by, so it means that our acceleration is equal to if we differentiate velocity by time, we will have acceleration. So it means that, okay, we will have, so now we should differentiate this part. Oh, maybe I now can use, oh no, it's something not good. Draw, I want to, do not need this one. What's that? What I should use? I know why he's do not want to simply draw. Okay. Chart. Okay. So it's working, but it's something I don't know what's happened that I cannot use this thing anymore. Some kind of selection, but I no need any. Okay, I no need any selection actually. Okay, yes, but you see, you see some kind of notation on my mouse, and it's not disappeared actually, and I cannot write. I know why it's appeared actually, and how it's appeared. Okay, I would try to write the text, but anyway, with text, it's not easy to to use some symbols. Yeah. Okay, so acceleration is equal to okay, maybe I can use some kind of symbols. I cannot use any symbols actually. Yeah, okay, so I will try to so if you write these expressions, I will try to end this whiteboard, and after that delta L, if we differentiate this part, delta L omega current and sinus become, so sinus function become cosinus function after differentiation. Become cosine omega t. And here we will have number of electrons multiplied by the charge Q. So now okay, Hudson. So now, if you remember from our last lecture, we said that for antennas we will use spherical coordinate system, and we will have meridian and azimuthal angle. So for electrical part, it's important a meridian angle. So meridian angle. So for meridian angle, we can write that our electric vector, or electric field of meridian part theta generally is equal to number of electrons Q charge A acceleration sinus theta, and here it's for P relative epsilon, relative permittivity, speed of light, and the distance at which we analyze our electric field. So now we should insert this acceleration into here. And after that, we will have 10 minutes, and after that, we reconnect it. So we will have such kind of equation. Number of electrons multiplied by the charge Q so if we insert it here, okay, I think that we can find it in our presentation. So now I switch off to the presentation. It's not this one. I need to share this one, sorry. Okay. So here you can see the expression 6.6. Of course, here we have some part which appear in some additional part, and this part belongs to the delay. Actually, because if we want to analyze in any point in the space the electric field in the meridian component of the electric field, so it means that at some distance r, we will have phase delay, and this part belongs to the phase delay. So here you can see we insert in the equation which I write on the dashboard, on a whiteboard, how it's called here in the Zoom, yes. So this Hessian dipole will be general expression looks like here. So it's for radiated electric field. So of course can be rewritten if we use some kind of notation of wave number, which we can extract from the omega and use some ratio, so wave impedance, which is equal to 377 ohms for vacuum or for the air. So hence the equation 6.6 become looks like this, and here we will have some ratio and insert not insert but change our wave number, so change the frequency into wave number. So again, here you can see that at any time we have some kind of a constant values which belongs to the constant value. We have length of our antenna. The K is of course depends on the wavelength. So, but wavelength again depends on the length of the antenna, because the exact length gives some kind of range of frequencies, and it means that it gives some kind of range of wavelength which antenna can radiate efficiently. So this here you can alternating current, the exact distance, and here the angle or in the meridian component, and phase delay depends on the distance. Okay, go further. So, but when we talk about meridian component, we should not forget about magnetic part. So, and magnetic part lies in the azimuthal angle, and you can see here that if we divide electric part from our impedance, we will have the part which is belong to a magnetic component. So notice how the magnetic component does not vary with the azimuthal angle. Hence, it exhibits circular symmetry. So last two equations suggest that the wave propagating from the Hertzian dipole antenna can be visualized as an expanding wave front centered at the antenna. In even more compact notation, you can find it in different books. So, but generally it will talk about the delay. So we can sometimes it will be expressed in which form it is written in many textbooks and or as a real part of the amplitude, or very general form which you can find with here is this phase coefficient, yes, or so phase coefficient um, or propagate, or so-called propagation constant. And here you can find the wave number or wave vector. Generally, it is very similar notations. Just only in some special cases they have slight difference, but generally here we can say that it's the same notation, so the same meaning but different notation. Okay, so next, so generally if we want to use some kind of practical from some kind of practical expression, we can see here that for after some substitution and some simplification, here you can see the 6.9 expression there. The K can be rewrite like this, and so generally alternating current looks like here we will have amplitude and here the phase. But now we should so these equations actually is some kind of fundamental building blocks for much of the work to follow. And so if we assume that our Hertzian dipole has accumulation of charge at the ends of the short wire and can be represented by allowing the dipole to be modeled as two charges with plus and minus charge placed at the ends of points of the dipole. So these charges of opposite polarity will oscillate as a complementary charge pair. So we can use this model to determine how the radiated electric field from the Hessian dipole behaves close into the radiator, close at the antenna. Unlike the far field region, so we have near field and far field. So near field, what it leaves around the antenna, and the far field, what is radiated in the free space. So in the far field, in this region, the antenna radiation pattern is a function of exact position of where it is measured. So we know that according to Coulomb's law, we will have such kind of expression for dipole. So now I will back to our whiteboard. Okay, so imagine that we have such kind of dipole, short dipole, yes, with a minus and plus. Okay. So actually it's now we can draw some scheme. Okay, so here we should imagine okay. Just a moment. So here we have y-axis. Yes, it takes time. Here we have z-axis. And just a moment. Here will be x-axis. Okay. So now imagine that here we have 1 point, and here will be, for example, another point. So here it will be plus. Okay, here will be minus. So now we choose the point in the space. We called it, okay, the P point in the space. So it means that we will have some kind of distance from here, some kind of distance from here, which is different, okay, and some kind of distance from the center of dipole. So you imagine that is very thin and straight, these lines, okay? So this point is P point. Okay. So here we will have the angle the angle theta. This distance will be R1. This distance will be R2. And this distance in the center will be R. Okay? So it means that this part can be write as a, so if we have here, if we have delta L, all length, so here we can write that the half will be delta L divided by 2. Okay? So this part and this part will be the same. So now, from this scheme, from geometrical consideration, we can express the R1. So the R1 will be equal to square root square root, I think. Okay. R minus delta L divided by 2 and multiplied by cosine theta. Okay, and plus delta L divided by 2 sinus theta or approximately it will be R minus delta L divided by 2 multiplied by cosine theta. So the same part, the same will look for what is that for R2? What's wrong? Okay, under it will look very similar, just with a R plus delta L divided by 2 and cosine theta. Okay, so it means that R2 minus R1, because we need the differences in the length between R1 and R2 will be equal, approximately will be equal to delta L multiplied by cosine theta. So if we want to so now if we know that the current is equal to current amplitude multiplied by sinus omega t. Sinus. So so our charge Q will be the integral how our current is changing during time. Okay, t, and it will be equal to current divided by frequency, angular frequency, minus sign, and here will be cosine omega t. So so now we should remember that our charge is observed at this point, at point P. So it means that we should use some kind of delay. So from this, we can write that our Q charge will be equal minus E divided by omega, and here will be cosine omega it's very difficult, and the delay will be T minus R divided by speed of light. So now we can back to the our to so here you can see that this part so now we should convert it our expression into spherical coordinate system. So how we can do it? We use this expression, yeah, and now you can see that this is part for the Cartesian coordinate system, the card coordinate system, but it can be equivalent to the spherical coordinate system. So it means that we should use such kind of form, and here you can find some part for component for R. This is the meridian component, and this is the azimuthal component. So according to this equation, when we differentiate this, we will have some kind of components for spherical coordinate system. Of course, for dipole, its most important part and the bigger part is a meridian component. So this part is rather small. Then we talk about electrical parts. This part is much bigger than this one. And due to that, in most cases, we can neglect this part. And this part is actually equal to 0 because this is magnetic part. The azimuthal component will be magnetic. So the 0 result is due to the symmetry of electric field in the azimuthal plane. So hence from equation 6.15 and 6.16, we see that an oscillating current moving in an infinitely small of wire will induce electromagnetic radiation. So comparing these results with the results obtained from 6.9, where it was assumed that R was a large distance from antenna, we see that close to the antenna, the one divided by the distance in the third order term determines the rate of decrease of the electric field in the meridian component with distance. So here the electric field created by a dipole dominates, and in this area the energy stored represents a capacitive region, which, since it is reactive, does not contribute to the radiated power. So it calls It's so-called near field. So in this case, what is important that if we come back a little bit, that this component represents that we have near field. So if we will have some part with 1 divided by r in the order of 1, it is usually indicate that what that we are in the far field, where this component is much bigger than the components with order of 2 and order of 3. So from here you can see that in the third part we talk about far field, and here we talk about near field, which is both exist. But for radiation, for us is important the first one actually. The far field is important for the communication, for the how we can translate the signals. So alternatively, if a short dipole is considered as a conductor carrying currents, then the associated magnetic fields can be found by direct application of Biot-Savart law, which states that the magnetic intensity at any point in an infinitely long straight wire is directly proportional to the current and inversely proportional to the distance from a point to wire. So here you can see that how it looks. And this is lies in the azimuthal plane. So here you can see that some component for the large distances, yes, the equation 6.8 now become, here you can see the part in the second order, which is indicate that what it will be near field. So the second term in the expression will dominate. It's much bigger, and r is rather small. And it is said to represent the induction component of the field close to the antenna. So inside this region, each of the field components is in phase quadrature. So with the energy absorbed each quarter of the cycle being returned to the field during the next quarter of a cycle. Those inside this region, energy is collapsed back to the radiating element and then returned to the region, giving rise to the antenna reactance. So it is again the near field of magnetic part. Okay, so and because in the near field of the antenna close to the radiator, this is a very important interface. So the near field will be when r is smaller than lambda divided by 6. We have like a capacitive field quantities for electric and magnetic field respectively. Outside the region, the energy leaves in the form of propagating electromagnetic wave traveling at the speed of light in the vacuum. The interaction of these fields results in a reactive quantity normally referred to as the near field of the antenna. So by applying Poynting's theorem, we get the instantaneous value of radiated power per unit area. So when we multiply electric and magnetic components. So in the antenna near field can be found in such kind of form. So okay, maybe you have some questions, and I this is, I think, all for today, but do not leave. I need to do print screen where all of every one of your information